Well, Richard Heck, Ei-ichi Negishi, Akira Suzuki, welcome to Stockholm and to Nobel Week.
Okay, thank you.
You, Professors Negishi and Suzuki, you've just arrived from Japan, where you were together, being feted. Do you enjoy all the attention that this brings?
Well, I think maybe I want to enjoy it.
How about you?
Well, I feel that it's part of the prize, and probably the best thing is for me to enjoy it, and then provide hopefully my best service too.
That's true. I suppose you can't escape it, so you might as well enjoy it. Yes. How about you, Professor Heck? Well, you were in the Philippines, so maybe that was a little quieter.
Already retired, yes.
Yes.
So yes, nobody found me there.
Wonderful.
Quiet.
You already, I suppose, must be used to some fame anyway, because the reactions for which you have been awarded the Nobel Prize are named after you. There's the Heck reaction and the Negishi reaction and the Suzuki reaction. So you are household words in any chemistry laboratory.
Only in the chemical world.
Yes.
Yeah.
But within the chemical world, very important words. I mean, there's so much of carbon-carbon chemistry is done using these reactions. It's a nice part of chemistry that, organic chemistry, that the reactions are named after their inventors. So all these characters live on through the pages of the organic synthesis textbooks. Do you know where that convention came from, that reactions should be named after the people who made them?
No, I don't. But there are several books based on so-called name reactions, and I had an occasion to go through some of them. And after the World War II, there have been just about 100 names given to 100 reactions. So that means maybe 2 a year. So
it's getting much rarer.
I'm not sure. So I suppose we are 3 lucky ones.
Of course, before the Second World War, some of the small number of the name reaction we already had. For example, these are the reaction. Such kind of reaction is a very long historical background. But as he just told you, after the Second World War, I don't know why, because one reason should be many reactions discovered by many organic chemists. That should be one reason. And another reason is name reaction is very convenient. For example, in my case, if I tell you exactly in the chemical world, that is a cross-coupling reaction of organoboron compound with organic electrophile. So that is so long word. But Suzuki reaction is very including all of such a things. So I think Professor Brown, because I just talking about when I visited when I met the Professor Brown.
This is Herbert Brown, yes.
Yeah, Herbert C. Brown. She recommended me to write my so-called Suzuki reaction. So I agreed. I started to write such a book. And finally, I named the book The Cross-Coupling Reaction of Organoboron Compound. Professor Brown said, no, this is not a nice word, nice name. Suzuki reaction is very simple and very convenient. But I against his proposal because I'm one of very small, shy Japanese chemists, So I don't like such a big, name reaction. I never want to join the name reaction. But Brown said, no, it's okay. But at this moment, I completely thanks Professor Brown because he gave me that. We decided, I published my book. The title of the book is Suzuki Reaction. That is now I'm very, thanks Professor Brown because it's very convenient to collect all of such the research from the journals, Suzuki reaction or say coupling reaction. Everything is I can correct such the chemistry, And in such a meaning, it's convenient.
It's a nice way to be made immortal, to have a reaction named after you, I think. So, if we turn to the cross-coupling reaction that we've just been discussing, it began with you, Professor Heck, in working at the Hercules company, I think.
Yes.
And you were exploring palladium's ability to do interesting things. You weren't actually looking for a cross-coupling reaction, were you?
No, I wasn't. No, it just happened. And I recognized it and thought this would be something useful, so that's why I studied it.
Were you, when you published papers on this, you published them as a single author, so which implies you were working very much alone. Was that the case?
Well, I had a non-technical assistant, but I only had to put my name on it.
So were you left free to play in this industrial environment? You could just.
Well, I was in their basic research group. It was just a small group that could try anything, I guess, if they thought it might be useful, and they left us alone pretty much, at least for a while.
And were you aware that palladium would act as a catalyst to bring carbon atoms together in this way?
Well, there were some things in the literature that suggested it might be a useful reagent for doing that kind of chemistry. Yes, it was. There were some early people in this field who did some good chemistry, like Coates. Remember Coates and Calvin? I remember that paper, which was one very early, but nobody ever seemed to follow it up.
Was your company keen to make money out of your research?
Well, that was what I was supposed to do. I don't think I did much for them, but that's one of the reasons I'm not there anymore.
But you weren't patenting the method or anything like that?
Well, they patented everything that they thought could possibly, conceivably be useful. Right. So some of it was patented, I think.
But it didn't stop everybody just taking it up. So.
No, they didn't seem to care whether they did it or not.
And the beauty of the Heck coupling reaction is that it's a relatively mild way of putting carbon atoms together, and therefore is hugely applicable because you can leave all sorts of side groups intact while doing it.
Yes, leave the functional groups alone. Yeah.
And its uptake now these reactions are everywhere, but the uptake wasn't immediate.
It's usual, though, isn't it?
Yeah, I guess. But when do you think its power was seen?
Oh, I couldn't put a date on it. It's a slow process. It just happens slowly. You have to make a decision on where you're going to say it started. I don't know. It's hard to say.
And then, Professor Negishi, you replaced the olefin part, the carbon-carbon double-bonded part of the reaction with an organozinc compound. And this extended the applicability of the reaction.
I guess I represent a rebellious group. So basically what we have done is took a cue from his reaction, replaced the hydrogen, CH, with a CM. CM.
Yeah.
So many people nowadays say, you went backward. Because hydrogen is a more agreeable element, generally considered to be more agreeable element than metal.
So he made it more toxic.
Yeah, potentially. But some of us, including myself, say, well, this is a characteristic of sort of a next generation group, including Professor Suzuki's Suzuki coupling. If I may say so, it's a tag. M is a tag to organic molecule. So here, you shall react here, or here, or here. We can specify cis and trans, here or here, cis or trans, and such. And it will also act as a major promoter. With having M rather than H. Eventually, I think we would want to go back to hydrogen again. But at the moment, we claim that by replacing original hydrogen with metal, now the rest can be virtually anything. And then with a tag and the speeding up the reaction from around 100 degrees down to room temperature or below, and then retaining all sorts of integrity of that group. We can specify cis by putting M in a cis position,
Yeah.
or we can specify trans by placing M in a trans position. So that's a
But it's very interesting
Yeah.
to hear this reaction talked about as a work in progress, that there is a current situation where you're dealing with CM, there is an eventual position where perhaps you can go back to CH. Because when I think they're talked about normally, it's as if they are things that have been given to the community, and this is the Heck reaction, this is the Negishi reaction, this is the Suzuki reaction, and they are to be used. And one doesn't think about their further development. But of course they are. They are developments of each other, and there is a continuation.
Yeah, I think that's our ambition. And our eventual goal is to be able to hook together any two organic groups. And we believe that we have covered a little more than halfway through towards this goal. But in each case, as I said, eventually it would be very nice to replace metal with hydrogen. But to what extent we can do is a remaining question. But before that, we want to be able to cover all types of organics and all combinations. Probably we have to take care of about 100 different combinations. And I believe we have reached just about a halfway point.
I want to pick up on this halfway point, because there's this marvelous abundance of molecules out in nature that we look at and try to emulate and sometimes build and sometimes try to improve upon. And then there are textbooks full of reaction schemes which allow one to think about how to put things together to make them. And you're saying that we're about, as an estimation, halfway towards the goal of filling those textbooks to the absolute limit. How does one estimate how many reactions there are to be discovered?
Halfway means, well, not necessarily in sort of volume of or the things that we cover. Typically, organic compounds, we can consider in terms of 10 or so dozen different kinds of functional groups. Alkyl, alkene, olefin, acetylene, aromatics, acyl, etc., etc. About 10 or dozen. If you take a look at the organic chemistry textbooks, then you see their discussions of them in dozen to 20 chapters. So that's organic chemistry. So if you consider 10 or so as R1 group, and then similar 10 or so as R2 group, then you have a 10 times 10, 100 combination. If you can hook them at will, as you wish, then that's the whole, essentially, practically the whole organic framework construction. You understand?
Yes, I do. Yes.
Okay, so forget about the other functional details. But in our approach, functional groups can be there, can be placed as needed. And then when time for coupling the two together, we do that.
It's a lovely. It makes organic chemistry sound so lovely and approachable. It's a 10 by 10 matrix, and that's it. If you can fill all the boxes.
I call this a Lego game.
Yeah. Okay. Yeah. It's just fitting the Legos together.
Two Lego game pieces.
Yes.
Then you hook them, and the critical one is the palladium.
That
serving as a
acts,
catalyst.
okay, so that acts as the catalyst. That is the thing that brings the Lego pieces together to touch them together.
So that's the main difference between what we do and what Grignard did 100 years ago when he won the Nobel Prize, the first Nobel Prize in organometallic chemistry. He didn't have the catalyst.
Okay, so
Didn't have the catalyst. But his is probably still considered to be one of the most versatile methods in organic synthesis. And I tend to feel that ours might supersede, might go beyond.
And that's because of the power of the transition metals.
Yes.
To catalyze. So tell me about the power of the transition metals. Here we're dealing with one, palladium.
Yes.
But there are...
according to my opinion, I have a little bit different thinking about chemistry. This time, I don't know, we get the Nobel Prize by using the cross-coupling reaction, using the palladium catalyst. But according to my opinion, palladium is not only one important transition metal catalyst, because palladium, of course, many people know palladium is a very nice catalyst, but unfortunately, that is very expensive. So nobody wants, especially in the company, they don't want to use such expensive catalyst for big amount. So recently, for example, in our reaction using organometallic compound, of course, when we started our chemistry, we first used the palladium catalyst, but not only the palladium, we also used the nickel compound and the other kind of the transition metal compound. But at that time, we found palladium give us the best result. Nickel give us some result, but sometimes they had the mixture of product, selectivity, that means the selectivity is no good. So I decided to student, we stopped to study the other transition metal catalysts except the palladium. We only check the reaction by using palladium compound. But after that, after my retirement, many people used even in palladium catalyst in our coupling reaction, not always give us the best result, because when we use a palladium compound, for example, the coupling reaction of aromatic chloride with aromatic boric acid is very difficult when we use a palladium compound. But recently, the people reported when we use a nickel compound as a catalyst instead of palladium compound, even the aromatic chloride reacts with aromatic boric acid to give a bifenil type of compound. That is one of big advantages.
So as well as varying the substituents that go into the reaction, one can also vary the transition metal catalyst, and then that just opens up a whole new spectrum of possibilities. The idea that we can solve all these problems of how to link the different functional groups together suggests that there might be an end to the development of organic chemistry, that that synthetic methodology could reach a point at which you say, right, we have what we need, and then it's just building what we need. Do we really foresee such a time?
In a very, very long time, long time. But this is only one mode of organic synthesis. Very, very general, very important mode. But I have been recently telling people, organic synthetic chemists have a major, major task right now, which we want to solve. That is how to convert carbon dioxide and water into carbohydrates, which nature does in a biochemical way, biological way. But no synthetic chemist has yet to, have yet to claim this laboratory way or factory way of doing the same thing. And I think this is a very, very important task, because if we can do that economically, which we should be able to do, then we will solve a food problem, energy problem, and the pollution problem, because the CO2 is the starting material. We need more rather than less. Yeah. And I say this, I cite this one because I believe, firmly believe, as in nature, D-block transition metals, in the case of biological process, it's iron. Iron is a D-block transition metal. Is going to be critically needed. And probably one electron transfer process, radical kind of chemistry, rather than our nice two electron transfer processes. Like a Heck reaction or a reaction. So those are all two electron transfer process reactions.
So you would promote the study of and research on the D-block transition metals as a major area.
Well, I'm just presenting this as an example of a major goal right in front of us. We want to solve this today, or maybe in a year's time or 10 years' time, And no one, right now, we have a feeling that we should be able to do that because nature doesn't. Nature has been doing that for billions of years. It's a big shame for the entire group, including ourselves.
Well, yes.
So what I'm saying is that this is just one of the major pending goals. You talked about our task being reduced down eventually to zero. I don't think that time will come pretty soon.
When you moved into organic chemistry as a young man, was it the desire to solve problems such as how to convert CO2 or other things that drove you there, or was it just a general inquisitiveness? Were you applied or just curious?
I enjoyed working with chemicals. I could do things and make all kinds of perfumes and things that interested me in the first few years of my studies, and I expanded on that, and it's useful to make all kinds of materials that you might want to use, technical materials, for example.
Were you a childhood chemist?
Yes, that was in my early teenage years. I started chemistry.
A lot of children make bombs when they're children.
I guess I did do a little of that, but not much.
Yeah.
So that was my start.
What about you, Professor Suzuki? What led you to chemistry when you were young?
Well, I think recently, I don't know, here in Sweden, in Japan, the people say young Japanese boys and girls, they never feel so much interest in the science, including the chemistry, the physics, and so on. But so this time, after I get the Nobel Prize, decided I received the Nobel Prize. I had a main chance to talk with press people. They said recently in Japan, the young people, they don't like the science and technology. But I think in Japan, of course, as you know, in Japan we don't have any enough resources. We don't have any petroleum. We don't have any iron resources. We only had coal mining resources, but that is located so deep place under the land. So it takes a lot of money to cut from down to up. So in such a meaning, in Japan, important thing is they make a very nice product. Then we sell such a product to all over the world. That is the only way Japan people will continue our country. In such a meaning, we have to say the young people, you have to explain our situation. And one way we can continue our Japan is two fields are very much interested in science and technology to make a very nice product to sell the thing to the world. So in such a meaning, I say the Japanese government and the university professor, we said such a thing to the young people. And he joined us to feel very much interest in our chemistry. Not only the chemistry, the science and the physics. But in such a meaning, I always say the other day I had a chance to talk with Prime Minister of Japan after I get decided I received the Nobel Prize. So I emphasized such a thing to our Prime Minister. He's also a scientist. He's the physics is his major, so he understands very well. But unfortunately, many of the such a people in our government, they don't understand much more about science and technology. So I think the first thing important in our government is to understand such a real situation and to give a lot of research money. Of course, at this moment, Japanese, our economical situation is very not so nice, even though I asked the Prime Minister, our government, they understand such a situation to support the science and the technology and to give research money for such a field and also the reasonable money to the education. That is very important. I just say such as government people recently, yeah.
It's obviously undoubtedly good for society that scientists, that young people move into science. Normally, such aims are not the thing that drives people into science. You realize that later, but as a young person, you're just probably following a curiosity.
Yes. Yeah, I don't know, but anyway, that is, I just explained the Japanese situation.
Yes.
But what is the situation in here in Sweden, or here in England, or here in the United States? Is the same thing? No?
So many different people and groups, it'd be hard to just give one single view of things, I think. I think it is very many different approaches.
But my friend, the American, says that the young people, they like very much to become the medical doctor and the lawyer. That is just connected with some money, That is a very serious problem, I think, We have to emphasize that we have to give our knowledge to young people. Money is not the only one thing we have to consider. So, but anyway.
Yeah, that's a good message. I don't suppose it was money that drove you to chemistry originally. What was it that made you adopt chemistry as your subject?
Well, as an elementary school kid, I liked math. Very crisp. Then I thought I was going to major EE, electrical engineering. Fascinating, electronics. Then I switched to chemistry.
Oh, really?
Perhaps for a little bit for money, because someone told me in electronic or electrical industry, the pay is not so good. So my motivation was very impure. But looking back, I think that I chose the right field for me, because it's not so mathematical. It's not like math. It's not cut and dry. And yet I didn't develop my liking towards biologically oriented, areas, because there were so many unknowns and so many nebulous kinds of things, and many things were sort of in between. So they didn't appeal to me. And now chemistry, is sort of in between. between two extremes. And I love that, and I think that this is an area where we can exercise our imagination, and we can have many useful discoveries in the development. And then overall impact is, that works for the benefit of mankind. And so looking back, I am very glad that I chose chemistry, and I am recommending this to many young people by saying that.
Sort of feet on the ground and head in the air, sort of thing.
Exactly.
Yeah.
Yeah.
Do you find that young people are coming to chemistry to a sufficient degree in the States? You've been teaching at Purdue for many years. Do you find that?
So, from our perspective, probably we are finding fewer and fewer younger people to be sufficiently qualified to be trained by us at the graduate level. That's what I'm mainly interested in. And that's been one of my concerns.
So they're no longer seeing it as a better paid alternative. Why do you think they're not coming?
Well, as you said, probably they are gravitating towards the areas that obviously look more lucrative. Well, one of my grandchildren, he is majoring in business, not chemistry, not science. Maybe for that reason.
I think you used the phrase that shortly after the award of the Nobel Prize, that you see the development of the work you've been doing in organometallic chemistry as searching for the truth. And I mean, that has to be an extremely appealing concept for any young person, but maybe chemistry is sold wrong. Maybe people coming into it don't see it that way.
Probably not. It takes some experience and experience of discovering something new, or in a sort of a rigorously scientific way, you make some developments. And these kinds of experiences will further excite you, to propel you to pursue along that line. And those are very, very exciting experiences, even today.
I suppose it's difficult. You have to get the rigor before you get the joy of the discovery. And that
seems that way, yeah. And in my case, perhaps in Professor Suzuki's case, we learned a lot of these kinds of things, how to maneuver through failures and difficulties, and eventually to come up with a success from our common mentor.
Yes, well, let's return to Herbert Brown, Professor Brown. What was it that he taught you?
I think he gave us many things that one thing I still I knew about he said, that is you have to study your research results should be on the textbook,
In textbook.
Yeah. So that means you have to find your chemistry just, new field of the chemistry. So if such a new chemistry should be appears on the textbook. So he always says you have to do your study, which appears on the textbook. And also, I often said the saying is a little bit different, but I always say the student, you have to do the basic, in Japan, we had a special box. In the box, we put the rice. We have jubako. How do you say in English, jubako? That is
no English.
That is a kind of the rice box or something like that.
A rice box?
Yeah.
Okay.
So I say to the student, you never do your study. Just inside of the box, just they pick up some rice or something like that. No, that is not our research purpose. Our research purpose is even your rice box is small, you have to make the new rice box. That means you have to find the new research results. Nobody saw try such a field. That is meaning is the almost same meaning. Professor Brown told me and I told my student. So I always emphasize the student. We have to find the new research field in our study.
I mean, people are very keen these days in saying that you should think outside of the box. But this is much nicer because you don't just think outside the box, you have to create a new box. It includes the discipline one requires, not just the kind of wildness of
Yes. That is nice. My Professor Brown, and in such a meaning, we had the same, feeling.
It's very nice.
I think. He said before he was young, he liked mathematics first, but my sense is almost same. When I was a high school boy, I feel very much interested in mathematics. So when I get in the university, Hokkaido University, first I want to study the chemistry in the Department of Mathematics of the School of Science. But at that time, when I learned the organic chemistry, our professor, the textbook, we used the textbook of organic chemistry written by Professor Frieda. He used to be a professor of Harvard in Boston, United States. That is very, very interesting. So I changed my major from mathematics to organic chemistry. The organic chemistry, of course, the division of chemistry, but the organic chemistry is so far from the mathematics, Physical chemistry is just near the physics and mathematics. Organic chemistry is so far. I changed so much my intention.
Herbert Brown was obviously an enormous influence on you as well, Professor Negishi.
Yes.
Is there something in particular that you remember about him that encapsulates his approach?
Well, there are many.
Yeah.
But I think he's a master of how to handle difficulties or failures and turn them into success. And I believe we all learn how to deal with those hard situations. And he had many, so usually he has many plans.
I suppose failure is really more frequent than success in science.
Seems that way. But in his group, the ratio of success to failure gets very high. And I eventually came up with my own saying for my group members. I say research is something in which we link success with success with success with success. In other words, when we fail, do it in Brown's way and minimize the time of failure or difficulties and turn that or switch to success. And I think we need to have this kind of intense attitude, in maximizing the success to failure ratio, as Brown did. And because we have the same amount of time every day, every year in our life, pretty much the same.
Yes.
I have benefited greatly from that sort of attitude and that approach.
Thank you. And lastly, Richard Heck, but working alone, maybe you didn't have a mentor, or was there somebody?
Well, I worked with Winstein first, where I got my degree. And he, of course, taught me physical organic chemistry, and I didn't follow that up. I got into more organometallic chemistry as I went into industry. So in industry, I tried to make money for the company mostly. So they were directing my work, more or less.
And then when you were teaching at the University of Delaware, what did you try and impress upon the students? Was there one message that summed up your...
Well, I guess what they came away with, it's a difficult subject and you've got to study hard if you want to do well in chemistry.
That seems like a good admonition to end the interview on. Right. Thank you very much indeed, all of you, for speaking to us, and I wish you the most pleasant of Nobel weeks. Thank you.
Thank you very much.
Thank you.
We enjoyed it very much.
Thank you very much indeed.